Good morning, everybody, and welcome to the Creo presentation this morning. For those that don't know me, my name is Colin Wakefield. I'm the Chief Executive Officer of Creo. Creo has been associated with Enapter for 2 or so years now. And prior to that, next slide, please. Prior to that, we and still are a manufacturer of specialist building products, products known as insulating concrete formers. These are Lego look-alike bricks that click together that form the shell of buildings, and they make highly insulated shells for low carbon, zero carbon structures. and also we have over the years deployed and experimented with air source heat pumps, low temperature devices, batteries, solar panels, and the whole gambit that makes up a zero carbon building. And 3 or 4 years ago, we started to build some experimental homes, and these homes were designed to test whether we could actually take buildings completely off of the grid and not have that dependency on grid for people living in these particular dwellings. What we discovered was that we had a deficit in the UK, that we couldn't power completely the whole building for the 12 months, and that we had to find something else to cover a percentage. Typically 20% we were looking for in terms of a deficit on energy. And then, next slide, please. And so we started to look for how we were going to extract this extra energy. It wasn't going to come from the solar panels. We didn't think batteries were a good economic route to go down. And we discovered that a company called Enapter were doing a press release in Thailand, and we decided to go. And during that visit, we witnessed Enapter showing how hydrogen could be created, could be stored from the use of solar panels, etc. So green hydrogen could be created, and they demonstrated. Next slide, please. They were demonstrating how we could perhaps cover our 20% of deficit that we needed for our zero carbon homes. So we decided to purchase a system from Enapter and install it into our research house here in the UK. And in doing so, we created what was the United Kingdom's first on-grid hydrogen solar-powered house. We've worked with Enapter over the last 2 years to develop their EMS, their energy management software system, so that we could integrate it into the systems we had in the house. So integrating it into inverters, into batteries, and looking at the whole process of generating hydrogen through a system-based approach. Next slide. And in this slide, you can see in the garden of the research house, we built a structure, and there we have the Enapter system, complete with other devices such as fuel cells, inverters, and some batteries. And that whole system is talking to the house itself. It's integrated. It's looking at how it's going to produce hydrogen. It's supporting the house and making sure that as far as possible, the house remains off grid. So it's a combination of devices, not just electrolyzers, fuel cells, and other products that we've integrated. And that system today is highly successful. Next slide. Here are some shots of Enapter's electronic management system. You can see that on the console left-hand side, and the middle one is a fuel cell, and then in our case Tesla batteries, which we've also integrated into the electronic management system, and then on the far bottom right-hand side some smaller batteries which power the fuel cell itself. So this whole system is completely integrated and working in harmony with everything else in the house. Next slide. And here are just some of the screenshots from Enapter's electronic management system, and you can see that we can control all of these devices, that we can see exactly what's happening with these devices, how they're performing, and what the state of each device is. So through this mechanism, we're able to control the house, and we can also do that remotely, of course, through the app, through the EMS Enapter app. We can also look at that remotely and monitor the house when we're not here. Next slide. The whole process of automation is critical to us because obviously we actually want to bring these systems to people that actually buy our homes and live in our houses, and we wanted it to be automatic. We didn't want there to be lots of things that people have to press or do, and so we're very happy today that in working with Enapter that we've been able to get their EMS system to integrate fully into the home, and we're going to move on from here and do some other exciting things. Next slide. So the next thing that we want to do, and the next thing that we are doing, is that we are attempting to run a level of artificial intelligence software sitting on top of Enapter's electronic management system. And in the research house that I'm currently sitting in, we do actually now have artificial intelligence running, and we're working with Enapter and their software teams to integrate that further. This should allow us to have far more automation. It should allow the interface of changing things to be a lot easier for the user. And we think this is the way to develop things moving forwards. Next slide. So what's interesting about our relationship with Enapter is that right from the beginning, you know, as a construction company, we knew very little about hydrogen. It's really impressive to me that in just a few short years that we've learned so much, that we've grown so much with Enapter. Their fantastic support has enabled us to do that. And as you can see today, we've got further projects that we're now pursuing in two critical areas. The first area is hydrogen storage, and we are now developing, and we're in the very late stages of producing our own hydrogen storage tanks, but storage tanks that come with somewhat of a benefit, because we are developing a coating that sits inside the tank that prevents the hydrogen from eating into the steel. There's an issue with hydrogen that attacks steel. It's called embrittlement, hydrogen embrittlement, and we believe that we've now managed to crack that particular problem. So later in the year, we're hoping to offer these tanks with hydrogen embrittlement protection, and which we understand might actually be the first in the world that someone's actually done that. In terms of forward development, we're looking at things like EV and hydrogen-powered fueling stations, and you can see some of our ideas and concepts on the bottom right-hand side. So it's interesting that we've gone in 2 short years from knowing nothing about hydrogen to pioneering some of the advances that we like to see in the marketplace. This has all happened because of teamwork. It's all happened because of collaboration and collaborating with other companies, and we're very keen to see that continue, both with Enapter and with existing partners and hopefully new partners in the future. Next slide. And I think, ladies and gentlemen, in the very short time we have, that probably covers what we've done with Enapter and the exciting prospects that we have going forward in the future. Thank you very much for listening.
Thank you, Colin. Very nice presentation. Thanks for being with us today and showing what your interaction and life is together with Enapter and all the challenges you have. Really appreciate what you showed, and especially on the artificial intelligence. There seems to be a lot of potential in doing that and integrate it into our existing software. Cool. So what I see so far is there's just 2 questions for you. And the first one is pretty easy. So they are interested in the supplier of your fuel cells that you showed.
Oh, the fuel cells. Okay.
Yeah.
Okay. Well, we work with a company called Intelligent Energy.
Okay.
And they produce fuel cells in the 1.5 to 4 kilowatt range.
Okay, Intelligent Energy, 1.4 to 4 kilowatt. Cool, thanks for that. And then there's another question for the construction project. The model is using solar and fuel cells to generate power and store it in Tesla batteries. Is that understanding correct?
Yes. So solar charges the Tesla batteries, and also hydrogen charges the Tesla batteries when required.
Okay, it's a mix of both. Cool.
Yes.
Okay, feel free to ask other questions if you have. Seems there's nothing coming in. So Colin, thanks again for showing that to us. And now we are planning to move over to George from Gap Energy in Greece. George, we're going to present your slides as well as we had challenges with Colin. So, but I will quickly bring up your slide. Feel free to introduce yourself if you like.
Good morning to everyone. This is George Palis from Gap Energy. We are located in Greece, but actually we are active all over Balkans and the Middle East. We have projects now in Saudi Arabia, in Oman, in North Africa, and of course in Greece. We are general contractors. However, the last 10 years we are focused in hydrogen. And we are working closely with the National Technical University of Athens to implement a hydrogen installation. Finally, after a lot of effort, we managed to integrate the hydrogen in their solar engineering unit. I dare to say that our first quotation for them was with EL 500, maybe 6 years ago. You mentioned that at the beginning. But finally, we installed the EL 2.1. So practically, if you want to go to the next slide, please, to have the presentation overview. We have to see what is the existing installation in the National Technical University of Athens. They have a solar engineering unit. Our target was to integrate the hydrogen, and we are going to see how this installation implemented on site. We will examine some of the local conditions. We will see the commissioning startup that took place before a couple of months, how we will implement it the EMS system, and we can see also some challenges and some conclusions. At the end, we can have again a small presentation of Gap Energy. Can you go to the next slide, please? So the the solar engineering unit consists of 50 kilowatts of PV photovoltaic panels. They have a wind generator of 2 kilowatts, and they want to integrate in this system a weather forecast module. Also, we integrated the H2 production, and the next step is to work with H2 storage. And of course, now we are installing a 2 kilowatt fuel cell. The future step is to create a hydrogen filling station for a small vehicle there in the campus of a university. This program is financed by a research program, and half of the hydrogen produced will go to feed the fuel cell, and half will go to the nearby biofuel laboratory for enriching the biogas produced there. We have to install some other auxiliary systems and some microgrid to implement the microgrid with smart meters. Let me say that this unit already feeds one data center, and the surplus of energy either goes to batteries already there or goes to the grid. Of course, they are not getting any money back from the grid, but it is a good example of an off-grid installation that easily can integrate it to the grid. Next slide, please. The main idea is the general configuration of an off-grid island setup, which is comprised of solar panels, wind energy, batteries, the electrolyzer, the storage of the electrolyzer, the connection to the local community, and finally to a hydrogen filling station. We had always in our mind that several, maybe hundreds of small islands in the Aegean archipelago exist, so might be a good idea, a few of them, to be totally green. One example of those islands is now implemented in Astipala Island together with Volkswagen, and they are trying to do there a complete green island. We hope to be part of this project soon with hydrogen. And next slide, please. So practically in this solar engineering unit, we installed two numbers of electrolyzer 2.1 and one dryer 2.1. The client covers the needs of purified water from their laboratory, but we are going to procure very soon and install one water unit. The time for delivery of those materials were approximately 4 to 5 months. As I told you, it took 5 years to proceed with the purchase order and the implementation of the proposal, but it was only 5 months to implement on site. The installation, the startup, it took about 2 weeks. To my experience and to my opinion, this was a very good example for everybody that has a small factory or a small residential unit that it is very easy to integrate and hydrogen production. Let's go to the next slide, please. Our team was very small for this particular project. Actually, we had only 2 engineers and 1 technician. It was more than enough. The whole staff came from Enapter, delivered in perfect condition. The packing was very good, excellent, I can say, professional by all means. It was very easy for us to receive it and to fix it on the rack 19 inches. Actually, we didn't put any effort to optimize the space of electrolyzers and dryers. Client, the university laboratory, asked us to be not optimized because it will be used also for academic training, and students should see around what is happening behind, in front, and up. So practically, we didn't bother a lot to optimize the space. The tubing was not quite easy to implement. Of course, if you have more units, you have to think more about the tubing, the stainless steel, and the plastics for water and the oxygen drain. Can we go to the next slide, please? We went by the book. We followed the Enapter's manual and toolbox 100%. We adopted all the recommendations for the materials and the small minor materials, either for tubing or for connector or compressor fittings or water tubings. I can say their quality was very good. Of course, the recommended parts were for, especially for stainless steel, were from Swiss-Loc, and I found them very good quality. Of course, I have used them a lot in the past for other projects. I'm coming from oil and gas industry. Anyhow, I found all the instructions given by Enapter's manual and handbook very well organized and very helpful to everybody to go on. Small details, of course, on site we elaborated together with Enapter support team. We could be in contact during the commissioning startup. We followed all the safety precautions recommended, especially we gave special attention to the oxygen line drain outside and the hydrogen pairs drain outside in different places. It was not very difficult. Of course, we installed a water trap, and in order to remove the condensates of water, and I can say it was not a small quantity. I think we have measured within an hour about 30 milliliters of water could trapped in this water trap. Part of this electrolyzer will not be only the production of hydrogen for electricity generation. It will become the whole installation will become a subject of training and execution of thesis of students. And one of the topics that they are going to investigate and study will be the removal of waters around. Yesterday, from the safety sessions, I realized how important is the purging of the lines. However, this will create one more complicated tubing, how you can purge the lines. Especially if you are going to install many units. For 2-3 units, it's not a big issue, but for a multi-core system, it will be more complicated. Can you go to the next slide, please? For the commissioning, we set up, we followed again all the manual and the directions. We provided the power supply from the system. It comes directly from inverters through a power panel, of course. We have a separate power switch box for the electrolyzers. And of course, we installed the application with the EMS software. Before the startup, we followed all the safety measures. We checked all the tubing for leaks and with salt water, as it is recommended, and as it is usually done in the oil and gas industry. We didn't have any specific problem. The Wi-Fi connection was there, and our devices very easily connected through Wi-Fi to our platform. Practically happened that period to be away of my team thousands of kilometers, and I was able through the platform to see their performance, to see the devices going on, and to see the production. Can we go to the next slide, please? Okay, this is the electrolyzer's final setup. As you can see, it occupies a very small corner in this laboratory. You can imagine that in this space it is about 100 square meters. We have already the batteries from the existing system, the inverters, and some PCs for the SCADA of the existing system. I don't know if you are able to run this video from your screen. I think there's a video there. You can see the application. We have a monitoring. We are monitoring all the production of the hydrogen, the temperatures, the production, the pressure, everything was there, and it was very, very amazing that how easy we communicated our system with the platform. Of course, we had always the technical support of Enapter's team. Can we go to the next slide, please? This is the video. So we practically, during the commissioning startup, we managed to have all the data acquisition, to have the remote startup, also the local startup. We tested all the functions locally, and of course the client was quite satisfied. Only he requested to include, to integrate the rest of the devices, like the inverters and the battery monitoring system, to the wind generator to our platform, which is something in progress. We are working on that. Finally, because it is an academic institution, they are using the software LabVIEW, and there was a question how we can communicate our EMS system to the LabVIEW. We are working on that, and we hope very soon we can communicate the two systems. Practically, they want to replace the SCADA, the local SCADA, with the LabVIEW. And this goes again to what Collins mentioned before. Everybody now is looking for some artificial intelligence. Everybody is looking for algorithms to control the generated power from PVs or wind generator, with all these fluctuations to be controlled through batteries or through hydrogen. And this is also our goal and our target. We are going to implement this. And let me take the opportunity to say this now, that it was a pleasure to continue after Colin. We met through the Enapter's integrators family, and now we are trying to collaborate in a demonstration of our projects through some European programs for getting more publicity and demonstrating that it is a very feasible way to install one electrolyzer and hydrogen production in your unit. Can we go to the next slide, please? So one of the main challenges for the next few steps, it is how we will integrate the electrolyzer and the rest of the system to an automation system, and to work as an off-grid power installation. Of course, the storage is something that it's a subject of our concern. Now, currently, we are using one small canister of 1,000 liters of metal hydride. This is very useful because you can transport hydrogen very safely in small distances, and but it is not enough. We are trying to see an efficient way to how to store more hydrogen, because our devices will can work for many hours per day, while we have a lot of solar power. So practically we need big volumes. Another solutions that we are working on that is to compress the hydrogen to reach 200 bar at least pressure. So practically we can feed even a small vehicle and implement a small hydrogen filling station. And this is a very good demonstration project for anybody who wants to see how these machines work in reality. So as a conclusion, I can say that we are very satisfied with the electrolyzers as delivered by Enapter in terms of packaging, in terms of delivery time, and in collaboration with the team. We didn't face any special problem because we followed exactly the manual of Enapter, and of course our previous experience with the oil and gas industry and the pressurized networks was assisting us to find proper solutions quickly. We believe that this demonstration project will attract more clients, especially from the private sector, because as I told you before, this was financed by a government institution, academic institution, but now more private clients are interested in this kind of installation. We have some meetings with them and to demonstrate our project. And we hope as soon as the legislation regarding the power storage by any means, either by batteries or by hydrogen, will be established within the next year. We believe before 2023 we will have the legislation in place. So practically the private sector will seriously see the installation, and we might have multiple systems very soon here also in Greece. And next slide, please. Yes. So as I told you before, GAP Energy is a general contracting company and trading company. We are mostly in general infrastructure projects in the oil and gas industry. We are working more than 25 years in this market, and we have dealt with hydrogen a lot in the past in the refineries, but of course it was hydrogen generated for refinery needs by methane. Now we are dealing 100% with the green hydrogen, and we are glad that we are part of this family of Enapter. We believe that we are in the proper time and place for the hydrogen momentum to take place and be implemented in big scale. I have finished my presentation. You can always contact us through the web or through Enapter, or whoever wants more information about this kind of installation. As I told you, we are active in Greece and the Balkans and the Middle East. Anyhow, we can find a formula to give you more information and to advise you about a potential construction regarding electrolyzers. Thank you from my side.
All right, George. Thanks from our side. Awesome that you shared all that information with us. Thanks for doing so. So there seems to be a lot of interest, especially for the region of Saudi Arabia. You mentioned that you are planning projects there. Can you give us some more details on that?
Yes, actually, in Saudi Arabia, we are working as consultants for main government projects, and lately we have involved in some infrastructure projects in Neom, new city is being building there in the north, and it is promoted to be the most green city in the world. Of course, they have found solutions about hydrogen. I don't know if there's any room for our hydrogen generation system. I think Air Products has planned a very, very big factory there. Anyhow, Saudi Arabia is a very big country, a very great kingdom, so there is place for everybody to install a hydrogen unit.
Okay, cool. Well said. And there's another question. If you can estimate from your queue, who are the main or the major end users that you have in the pipeline? So far, you implemented that project with the university, but I expect there's a lot of things in the queue.
Yes, one of the next customer will be public power company of Greece. We have already installed one fuel cell for them, two fuel cells for them, and we simulated the production of hydrogen because it was not available the budget there. And practically we feed the fuel cells through bottles. And the next potential customer were a part of the public power companies, the refineries, because both the two big refineries in Greece, they want to go greener, and they are looking very carefully now to hydrogen production. Of course, always the three of them are very big players and are looking to megawatt scale. So we are going to see something of a multi-core installation.
Okay, very good. Thanks for that. And then there was another question. If you can share your contact details, it's on the screen. I think it's answered with that. That should be fine. Okay, perfect. Thanks again for sharing that. And the next presenter we have is H2 Core Systems from Germany. So Mark, it's on you now.
Okay, so I think I was able to do screen share. You can see my screen.
Yes.
Perfect. I can't turn my camera on for some reason, but I guess it doesn't actually matter, huh? Okay, so morning, everybody. Thank you for your time and attention so far. I work for H2 Core. H2 Core is a German manufacturing integrator company specializing in the design, assembly, implementation of fully integrated hydrogen systems. We have built our sort of product set and our portfolio based around the Enapter AEM module. I'm also joined by my colleague Thorsten Clausen, who's online, and we're both happy to answer any questions you may have. So I guess the fundamental challenge for many projects really is this Achilles heel of how we deal with storage. So in terms of hydrogen storage, there's a certain element of complexity and cost for the variety of storage options that can be used, particularly for many smaller scale systems. And more so where these systems are in areas like metro or residential or highly populated areas where you have space and, more importantly, security and safety type concerns. Less so if you're going to a remote place in the middle of the jungle, you have less people looking over your shoulder. But in terms of the storage element, I mean, in many cases, we find that the cost of storage can be as high as 40% of the total cost of the system. So while the Enapter AEM is nice in that it produces hydrogen at 35 bar pressure, and indeed that can be fine for many applications, we do provide low pressure 35 bar storage solutions in single vessels, which can be as large as 115 cubic meters, which could hold 325 kilograms of hydrogen. But being practical, a vessel of that size would be typically 40 meters long and weigh about 39,000 kilos. So the picture, I think, on the top left here, this represents a project we were looking at for a residential application in Europe. So basically, this user has lots of solar on the roof. Their solar downside, if you like, is only for 3.5 months of the year. So for 8.5 months of the year, they're able to produce hydrogen, but then they need to use that in 3.5 months. And based on the sort of the volume of hydrogen and the kilowatt hours that they require during the low PV season, it would require them to have a tank, which would be basically almost 4 times as long as the cabinet that the system would be in. Now, that's obviously a little bit impractical for a residential type application. We did suggest that the tank could be mounted upright, but the problem in that case would be that the vessel itself would be physically taller than the house. So the option of compression storage obviously has to be considered, and the solution in this case was a compressor which we were able to build into the cabinet. I'll explain more about how that compressor works, a buffer tank, and then using sort of high pressure vessels in racks to deliver the storage. So from a footprint space perspective, in this particular case, the compressor option overran, well over the option of just using low pressure vessels. So our approach to fixing the problem of storage really is sort of addressed in a number of ways. So we do provide solutions that will cater for Enapter's production process of 35 bar. We do provide storage solutions to suit that. But we've worked very closely with a number of, shall we say, compressor or pump manufacturers, in particular Maximator, Sauer, and High-T. And basically, they will provide us with the sort of the piston, the mechanical element technology, and we build the balance of plant around that. And in terms of the sort of compressor options, they could be electrically driven. In some cases, you may not want it to be electrically driven. They can be compressed air driven. And we're also working on solutions that use membrane approach, a bit like the electrolyzer itself, to transfer hydrogen from low pressure to high pressure. Our designs, wherever possible, we want them to be cabinet based, and our cabinet and our building block is basically a 19-inch rack type design in a 2-meter tall cabinet. And we offer the cabinet in 2 forms, either an outdoor cabinet or an indoor cabinet. And for countries such as, say, Northern Africa or India or places like that, where the temperature can exceed 40 degrees, our outdoor cabinets would have an air cooling system to maintain that the ambient temperature. Where possible with cabinets, our approach is to sort of use the sort of concept of adding more cabinets rather than going into a container type space, because we find cabinets are a little bit more flexible in terms of allowing somebody to grow their system from, like doubling or tripling the capacity is easier to do by just adding more cabinets than it is by adding more containers. And in terms of the storage technologies that we want to support or we need to support, obviously they're pressurized vessels, and also more recently metal hydride. Metal hydride does solve some problems, all right, but there are issues to be considered with metal hydride, where if you make a mistake, your metal hydride can be severely compromised. And the storage solution of choice, low pressure compressor, high pressure, or whatever, is purely really based around the application use, whether it's residential or business, whether it's metro, a built up area, whether it's remote area, whether the application is for refueling, manufacturing, load dumping for utilities, for example. And finally, and this is a topic in its own right, a lot of the design is also sort of directed by the local safety and regulations, which vary from country to country and even from region to region. So in overall, the sort of compressor options we have, they all seem to be named after DC comic characters, but the solution that we would provide for a small system, which could be, say, a signal cabinet with 2 electrolyzers, would be what we call our Aquaman. Physically, the Aquaman is the size of 2 EL 4.0s, so it fits nicely into our 19-inch cabinet. The compressor itself is actually contained in water. So the box itself has got a water tank, and the compressor sits inside that. And the advantage of that is we get no noise and no vibration. So it can quite easily, quite comfortably sit inside indoors. It doesn't have to be outdoors. So that is a solution that we see is very practical for, if you like, small single cabinet with 2 electrolyzer type solutions. The flow rate of Aquaman is about 1.2 cubic meters per hour. So it'll quite easily deal with 2 electrolyzers. And if you want more, you just add more Aquaman. The next model up is basically a scalable compressor that we've developed with Maximator. And it's basically got, it's a modular design type system. So the unit at the bottom is like a power and controller type system. And then each module allows you to step up your compression in stages. So the first module will allow me to go to 140 bar, second module up to 400 bar. And also we can grow that further to as high as 1,000 bar if necessary. Then for other sort of more larger scale type applications where the flow rate or the transfer rate needs to go from, let's say, 7 cubic meters up to as high as 48, we use the Mercury and Cirrus type compressor design. And these were a little bit more complex because they're physically larger. And but it's really sort of no upper limit, I guess, in terms of the type of compressor. Generally, it really depends on the country in question, but 300 bar seems to be the sweet spot in terms of cost and complexity. Going much higher than that, it's almost substantially more expensive and definitely more complex. So we've combined both the compressors and the electrolyzers into a container system really designed for refueling applications. And this is a product that we make that we have available to integrators and partners. Some of them use it for as a refueling station, where we've incorporated a dispenser with this as well. And some of our partners also combine it with a fuel cell, so it becomes both a refueling station and, if you like, a potential backup power system as well. So in terms of the examples of this, we have deployed a number of these systems pretty much around the world. But in terms of the nicest example of the compressor type design and how clean this can look, I'm going to point to our recent deployment in the College of Weimar in Germany. I think it's got to be the nicest, cleanest installation that we've done. And also from receipt of order to delivery of the system, including the storage vessels, compressor, ELs, whatever, was approximately 5 weeks. So everything happened relatively fast. Yeah. So I guess the requirement that we were initially trying to address was a college that were implementing hydrogen as part of their syllabus. They didn't really have much to start with. They had an empty room, which we had to advise in terms of converting that to support the equipment itself. They wanted the compressor to be indoor, and they wanted to start basically small and then have the ability to double up or increase the capacity both of the hydrogen storage and of the compression side. And one of the reasons for that really was that the object of the system, the function of the equipment, was more as a sort of research platform for their students to measure things like efficiency and production rates and stuff like that. So in the solution we delivered basically would be our standard indoor cabinet. This is with liquid cooled electrolyzers, and they wanted liquid cooled because they were able to better measure the efficiency in terms of temperature loss and stuff like that. And we provided them with a half-size cabinet, which allowed them to go up to 300 bar, with the option to upgrade that by adding another module, which basically claps down on top of the existing cabinet. This is, if you like, an overview of the room. I wish I had a picture of the room before we started, but you can see they have a treated floor. The blue lines here, these are the liquid, the cooling lines for the ELs. These silver pipes on the roof, that's the negative pressure ventilation system. So air is drawn out from the top, and it's put into the room on the floor level, and the room maintains a positive pressure all the time in case of hydrogen leaks or whatever. This is the piping that goes from the base cabinet to the storage, which is outside. Beautiful job of workmanship. The two thick lines at the top, pipelines at the top, are the compressor, the line into the compressor, and the return line from the compressor. And the return line from the hog compressor, in this case, also has the hydrogen purge included in that. That red object at the top here is a gas alarm. By law, it has to be a combination of a horn and a light. And this silver thing beside the cabinet here is actually a silencer system for the ventilation, to stop the ventilation system, bothering too many people. So if I go outside, for the initial storage, because they're operating at 300 bar initially, we're provided them with a 12-bottle rack rated to 400 bar. This is fairly standard product. It contains 12 bottles to standard 50-liter vessels. But as a general sort of observation, getting our hands on steel vessels these days is very problematic, partly due to the fluctuating price of steel, but we do stock these in many cases. The little tube with the yellow cap on it, that's a safety blow-off valve. The cabinet on the left here contains the air compressor, and the air compressor is designed to match the output of the ELs. So if the two electrolyzers produce 1 cubic meter per hour, the air compressor, we have a buffer tank, which is actually also inside this this cabinet with the compressor. The buffer tank is one of these 50-liter vessels. And basically when the EL fills the buffer tank to 30 bar, the air compressor comes on, opens and starts transferring from the buffer tank to the high pressure vessel. When the buffer tank drops to 20 bar, the air compressor switches off. So the transfer rate is really designed around the hydrogen production rate, which is 1 cubic meter per hour. This is showing the lines on the, coming from each of the cabinets. They're on the floor. If anybody can tell me what that orange thing is in the picture within 15 seconds, we will give them a free EL 2.1. So I'm going to wait for 15 seconds. These obviously the blue line is the water line, the water coolant line coming out of the ELs, and that's basically it. It's all swage lock, all 1/4-inch piping, and minimum amount of bends and T pieces where possible. So if nobody has found the answer to that orange box, what that orange box is a small little pump. And the inside the system, inside our cabinet, we have designed a water trap system with a expansion vessel. And normally, if this system was outdoor, we would allow the water that's collected, the water that's collected in some of the lines, we would allow that just to dribble outside. Because it's inside a room, we use this small pump to transfer the sort of water that comes out of the purge lines, the condensation water. We use that to pump that out of the room. It's an option that we can provide. This is the plumbing, if you like. So coming from the room down here, from the hole in the wall, the hydrogen vent line has to go obviously past the building, so 1 meter high past the tallest part of the building, and that is probably our cleanest, nicest installation. So in conclusion, I mentioned before, we do a range of systems based around the AEM. These include like pure hydrogen production systems. In the picture here, I have 5 EL2s and a dryer in a single outdoor cabinet or indoor cabinet option. This can produce 5 kilograms per hour. We can cluster these. We can put this in a rack and put the racks inside containers if necessary. We can combine the hydrogen production with fuel cells. The fuel cells we use for the smaller systems are generally from Intelligent Energy, just simply because their form factor is perfect. However, we have to be fuel cell agnostic, and we've also worked with other fuel cell manufacturers such as Proton Motors, PowerCell, NedStack, just to name a few. The compressor solutions, as I mentioned, Aquaman is not pictured here, but Aquaman is available for the smaller type applications. For larger, we go for the Hydro Hulk, where we can go up to a variety of different bar pressures. We can also support larger systems. We can implement these in the form of, dispensing or refueling stations. And we've also done some, work around the multi-core product as well. So we basically serve partners, and these partners are the people who engage with the end customer, who determine with the customer what the solution is, and we basically manufacture the solution for our partners. Now, our partners can also include, and do include, Enapter partners. So if you're an Enapter partner and you have a project, we stock all the items. We can build your solution. You can put your name on the front. We understand the technology, and we can very quickly deliver the actual solution to your customer. As I mentioned, we have most of the equipment in stock. We have ELs in stock. We have cabinets in stock. Fuel cells may take a little bit longer because a lot of our fuel cell suppliers do have chip and component problems, but we also try to stock fuel cell modules. So we can pretty much build the system that you need in much faster time frame and do it relatively inexpensively, where the partner receives a system that's been built under quite strict compliance standards. It's already been commissioned, so you just have to turn it on and connect all the piping as necessary. Yeah. So finally, I think my 15 minutes is up. My contact details are here. Also, my colleague Torsten, who's our head of engineering. So please feel free to contact us if you have any inquiries or you have any projects you need help with. And I think that's me.
All right, Mark. Thanks a lot. That was pretty interesting. And thanks, Torsten, for your correction in the chat that it is 5 kilograms per day and not per hour.
Per hour.
So that's clarified already. Perfect. Thanks for that. Nevertheless, we got some questions. So are you ready for some?
Sure.
Okay. So the first one is on the H-port system that you showed. Is that ready for supply? And if you have any references that could be visited?
Sorry, you said that the what system? The
H-port.
H-port.
Yeah.
Yes, I would. Yes, it's already provided. It's the container system. So I think we probably need to bring you to a site to see one. Yeah.
Right. So in this case, they directly contact you to get an arrangement, right?
Yeah.
Okay.
Correct.
Perfect. Yeah. Okay. And then there was somebody looking for the costs. So he mentioned that H2 storage is 40% of the total project cost, which seems to be a bit high. And he's asking if that is covering already transportation, groundworks, and so on, or if that is additional.
No, that's additional. And when I mention these figures, it does vary really depending on the requirements. So if I go back to that example of, if you like, large scale storage, because I need hydrogen for 3 months of the year, that's quite a big storage system. So it will vary. But I guess what I'm sort of saying in general is the combination of the price of steel, the vessel, and the compressor is quite a large piece of the cost. If you go for much larger systems like multi-core type size systems, the storage might drop from 40% down to about 25%. That price does not include the logistics of getting it anywhere. Yeah? That's just the material, the bill of material, or the component cost.
Okay, that makes it clear. Thanks for that. Another question, and partly you answered that already. So first part was the manufacturing of the fuel cell, which you mentioned intelligent energy due to the form factor that fits well into the cabinet.
Yeah.
But there's another question on the manufacture of the inverter to connect the fuel cell.
There's a variety that we can use. If it's a remote location and you need something, you need a Range Rover, I would probably say look at Victron. But to be honest, there many off-the-shelf units would be fine. Yeah.
Okay, good. Then a very special request: if H2Core can provide service to Asia Pacific countries. So if you deal in that market already, or if you want to.
Well, people ask me where I'm based, and I tell them I get my laundry done in Indonesia at the moment. So I don't live in Germany. I live in wherever the activity is happening. So I'm based pretty much full-time now in Southeast Asia. I regularly go to Philippines, Thailand, Vietnam, Indonesia, Malaysia.
So that sounds to be a clear yes.
Yeah, it's a very much a yes. Yeah.
Okay, cool. Then a longer question, let me just check what we have there. So in India, we have some places having ambient temperatures of about 48 degrees during summer. However, as per Enapter's AEM cluster project document, on a certain page, the container shall always be maintained between 5 to 45 degrees Celsius for proper functioning of the system. In that case, we cannot use blowers for primary ventilation, as the ambient temperature outside is itself higher than 45 degrees. Now, if we intend to install AC systems in such situations, then for a system of 40 electrolyzers, the heat load dissipated will be 200 watts times 40. Okay, I think that's ending up in a long calculation. So we are going to take that and get your feedback on that later on. Didn't expect that, sorry.
Well, I'd
Good.
like to compliment the person who asked the question. They obviously put a lot of thought into it.
Absolutely. And
Yeah.
it will be answered, but not
Yeah.
directly.
I
Okay.
think the answer to best way to answer his question is we'll be able to show you something in India very shortly. So it's a similar problem in that the location in India, they experience temperatures almost as high as 50 degrees. So this is back to this quandary. Do I stick it in a container or do I put it in a cabinet? So the requirement in this application will be, if I remember rightly, 40 electrolyzers in 8 outdoor cabinets. Now, if I have a cabinet and all my electrolyzers are running, I will have airflow automatically being sucked in and going through the cabinet anyway. But to handle the anticipated higher temperatures of above 40, each cabinet has a bolt-on air conditioning system to get that temperature down. So the electrolyzers are okay, even up going past 40. The problem is their power supplies. Their power supplies can get quite upset if they're run hot. So we do have a solution for that. It's easier if the solution is implemented on a per cabinet basis than having, like, say, a 20-foot container, and you've got to try and manage the temperature inside a container using some form of heat management system. It becomes a little bit more complicated, in my opinion. Now.
Okay, thanks for offering that. And if you have use cases in the area, they should just reach out to you and get some arrangement on that done.
Yeah.
Okay, and then there is a last question from Akshay. Dimensions and weight of dryer and water tank, if you have that handy. Otherwise, we can answer that later as well.
I don't have the, off the top of my head, I couldn't tell you what the dimensions are. I can only tell you 19 inches wide.
Okay, and I see Philip is already providing some of the of our existing documentations, which includes dimensions as well. Perfect, thanks, Philip. Okay, no other questions for you, Mark. Thanks again for doing the presentation and for sharing your contact details. I have one last question left for Colin's presentation, if he is still around.
Yes, I'm still here.
Oh, great. So there is a person asking if your project, so your house, is existing. So I would answer that with a yes, just need your confirmation, and if it can be visited.
Yes, it exists. It's here. It's functioning, and we will take visitors. We do regularly. So if they'd like to contact me, we can make arrangements for them to visit.
Wonderful. Okay, cool. Then thanks again, Colin, George, Mark, for presenting your use cases, giving us all your insights. Thanks a lot.